Well, hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you out with number, which one is this? 21. Okay, in your homework, unit 3. So, let's see, it says, part A, find a symbolic expression for the EMF induced in that coil shown. So here's, right here is what they're talking about, all the action that's happening here. We have a current loop here, we have a loop. And you see there's an area here that's got a bunch of magnetic field lines going through it. So there's a magnetic flux through that loop. Now, remember that magnetic flux, when you calculate it, is field strength times area times cosine of the angle between the normal and the magnetic field vector, right? So here, the normal, you could think of it as basically same direction as the magnetic fields. So this is going to be a 1 here. The area, right, this is a circle, so we can put either area or pi r squared. It says radius r, I think I would do that. Now, one thing you have to realize is that these magnetic fields are changing. The field's getting stronger. It's going from 0 to some value, right? So to try to answer this question, the magnitude of the induced EMF you get by Faraday's law of induction, right? It's the rate at which the magnetic flux changes. So that's going to be a delta phi over a delta t. Now, when I write this, this is per loop. If there were 2 loops, you'd multiply it by 2. For 5 loops, you'd multiply it by n. For n loops, for 5 loops, you multiply it by 5, but for n loops, you just do this. Okay, now, your change in flux. This is your final flux minus your initial flux. The initial flux will be 0 because the magnetic field starts at 0. And then the final flux given in the problem, and then it says divided, let's see, in t seconds. So there's your value for this, and that should get you going on that. Okay, part B, looking down at the xy plane, is the direction of the induced current clockwise or counterclockwise. So that's a Lenz's law question. Remember, nature hates a change in flux. The induced EMF will always be such that it will oppose the change. The magnetic field vectors are in the minus k direction in this picture, and they are getting stronger. To oppose the change, ask yourself, what direction would the induced magnetic field need to be? And once you've answered that, then say to yourself, which current direction, this way or this way, gets me that field direction in the interior. So that should get you through this problem. I'm just going to end that there. Have a great day.